can stay further away from me if you want to be safe. Okay. So in this lecture, we will talk about polyhedral theory. As I said, throughout this class, we will proceed as follows. For each of the new topic we introduce, we will first talk about applications. Then we will talk about some mathematical property of this particular optimization problem we want to deal with. Then the last thing we will talk about will be the algorithms, right? So why do we care about the theory of polyhedral? So polyhedral is a types of set AX greater than or equal to B that describes the feasible region of a linear program, okay? And the reason linear programs are so different from general convex problems is because the unique geometric properties of those polyhedral set. So that's why we want to spend one lecture talking about the geometric property of the polyhedral set. So you could spend a whole semester just focused on polyhedral theory, but that will not be the focus of this class. So if you want to know a bit more about polyhedral theory, you can refer to the linear programming references. Right? You could spend the full semester reading that book. Okay, so we will give you some of the important results in polyhedral theory in this class. We will only do maybe 2 proofs, which are very similar. For the rest of the theorems, we will give you the result without showing you the proof. Okay. So first of all, what is a geometric intuition of getting the optimal solution in a linear program? Right? Remember this farmer planning problem we talked about in the previous lecture, right? Remember the feasible region is this particular polyhedral set, right? And very curious, the optimal solution lies on a vertex of this polyhedral set, right? So why that is the case, we will show you a theoretical reason why if a linear program has finite optimal objective value, then there always exists an optimal solution that is a vertex of this polyhedral, okay? Yeah. So we'll talk about some mathematical treatment, give you some geometric intuition of a concept like vertices, faces, rays of a polyhedral set. Those concepts are central to the development of a simplex algorithm, right? So those geometric concepts are developed by the mathematicians. Then the operations researchers come into play, and then based on those geometric properties, they can design an algorithm to solve linear programs. So maybe after this lecture, after you have seen the geometric properties of linear program, you can perhaps reinvent simplex algorithm yourself, right? Basically, simplex algorithm is a smart way of enumerating vertices and then find the vertices that give you the best solution of a linear program, okay? But first of all, you need to know why a vertex can give you the optimal solution. Okay, as we said before, what is a polyhedral set? A polyhedral set can be described in the form AX greater than or equal to B, where A is any arbitrary m by n matrix, and B is a vector with a dimension m, right? So as we said in the previous lecture, you can convert any representation of linear program into this general form, right? So we will use this general form as a general treatment when we introduce different theory, okay? And similarly, as we talked about in the previous lecture, the set AX less than or equal to B is equivalent to AX greater than or equal to B, right? It's just a different way of representing the polyhedral set. And similarly, you can use this standard form, right? AX equals to B, and then all the inequalities are greater than or equal to 0, right? That's what we talked about in the last lecture. How do you translate any linear program into this standard form? Yeah?
So it never states that A is a matrix of real numbers, so can it also be imaginary within A?
Oh, yeah, that's a good point. All the matrices we deal with in this class are real numbers. We won't talk about optimization problems that involve complex numbers. There are actually some recent research in that area. Okay, and then a polyhedral set can be bounded or unbounded, right? So this is a very trivial example of a bounded polyhedral set. It's a triangle. Right? And then here you have an unbounded polyhedral set, basically the first orthant in 2 dimensions. Okay. Just a brief review of some of the concepts we learned before. What is a hyperplane? What is a half space, right? A hyperplane is a set X in Rn, and then A transpose X equals to B, right? So that means the points have to lie on this hyperplane here. And AX greater than equal to B is called a half space. Right? Okay, that's basically this set here. So now, first of all, I will introduce some definitions. Because we talk about concepts like vertices or extreme points. So what does that exactly mean mathematically? So I will give you some mathematical treatment of how do you actually define a vertex. First of all, I want to introduce a concept called extreme point. So let's say let P be a polyhedral, and then a vector X, or you can think about X as a point or a vector, is an extreme point of P if we cannot find 2 vectors or 2 points, both different from X, and the scalar lambda such that X is a convex combination of Y and Z. Right? Okay. That's what you can explain in words. If you have a point, you cannot find 2 points which give you whose convex combination gives you X. Right? So here, as you can see very easily, the points A, B, C, D, and E in this polyhedral are extreme points. You cannot find 2 different points whose convex combination gives you that particular point. Right? And those A, B, C, D, E are like what you quote vertices of this polyhedral, right? So, but mathematically, they are defined as extreme points. And then I will show you what is a vertex in the next slide. So here, if you consider a point in this polyhedral set, like F, it is clearly not an extreme point because F is a convex combination of, you can easily pick 2 points, H and G, whose convex combination give you F, right? So now, what if I pick a point on an edge of this polyhedral? That is also not an extreme point because if you pick any point here, it is a convex combination of E and D, right? Only those so-called vertices are extreme points. Yeah. So now I will define what is a vertex of a polyhedral, right? We intuitively, you can quickly visualize what is a vertex, but then there is also a mathematical definition of a vertex, right? So let P be a polyhedral. A point X star is a vertex of P if there exists some C such that C transpose X star is strictly less than C transpose X for all the X satisfying X in P and X is not X star. Right? Okay, let's look at this definition a little bit. Right? So what does this definition mean in words? That means if you have a point that is part of the polyhedral, and then if you can find a half space, right? So C transpose X is like a half space denoting one way of the half space, saying that all the polyhedral is on one side of the half space, and then there exists a single point of the polyhedral that is on this half space. Okay, again, the whole polyhedral is on one side of this half space, right? But there is only one point in this polyhedral that is on this hyperplane defined by C transpose X star. Okay? Yeah. So intuitively, you will find out that a vertex is equivalent to an extreme point. Right? We will show you why that is true in a mathematical rigorous way. Yes?
So why do we use two different definitions for vertex versus extreme point?
Yeah, so those are the, when you talk about math, first you need to make some definition on the concepts you are going to play with, right? Maybe in some other sets they are not equivalent, I would assume. But in polyhedral set they are equivalent. We will, yeah.
Vertices are not extreme points.
Yeah, could.
Something like that.
Yeah, could be. Yeah. So, but I can get back to you in the next lecture. I don't have something on top of mind where, for what type of set where vertices is not equivalent to extreme point. Okay. Maybe for some non-convex sets. Okay. Yeah. But then we give those definitions, then we will show they are equivalent in the context of a polyhedral set. Okay. So another remark here is it is very difficult to verify if a point is an extreme point or a vertices, just by its definition. Right? So here, for example, if I give you a point, you know that point is in the polyhedral. If you want to verify if that point is an extreme point, you need to show that any possible combination of two other points cannot combine to be that point, right? That is not so easy to show. And then for a vertex, you need to find a hyperplane to separate this point from the rest of the polyhedron, right? So what will be a sort of more engineering way of doing that, right? Since let's say I give you a polyhedral set, how do you quickly give me all the possible extreme points, all the possible vertices of that polyhedral set, right? So that's why we will define this definition called basic feasible solution. It is much easier to verify than these two definitions of vertices and extreme points. And then we will show you these three concepts are equivalent under the context of a polyhedral set. Okay. So before we define basic feasible solution, we need to define something called active constraints, right? So let's consider a polyhedral P defined in terms of M by N matrices and vector B, right? AX greater than or equal to B. We see that a given constraint, AI transpose X greater than or equal to BI, is active or binding if at this particular point X star, AI transpose X star exactly equals to BI. Right? So if this constraint is not binding, that means AI transpose X strictly greater than BI. Right? But if it is equal to BI, then that means this constraint is active. Okay, that is the meaning of the active constraint, meaning that the inequality constraint actually strictly hold as equality. Right? That is the definition of an active constraint. Okay. So here's an illustrative example of active constraints. Right? So let's say if I pick a point, an extreme point A here, right? So how many active constraints are there? 2, right? So here, as you can see, at this point, these two inequality constraints are strictly active, right? Or they are active, yeah. So at this particular point here, only one constraint is active, right? So as you can imagine, this is an illustrative example in 2D, right? If you have two linearly independent active constraints, right? You have two equalities that will uniquely define a point in 2D, right? In n-dimensional space, if you have n linearly independent equations that also uniquely define a point, right? So that's sort of the definition of a basic feasible solution. So which we will show in the next slide. So here, let's consider a polyhedral set defined by linear equality and inequality constraints. Right? So here we say X star is a basic solution if, of course, if X star wants to be feasible, all the equality constraints has to be active, right? Otherwise, if the equality constraints are not even active, then you are not violating, you are not observing all the constraints. And then the other condition you need is out of the constraints that are active at X star, there are n of them that are linearly independent, right? So for all those active constraints, there are n of them that are linearly independent that uniquely define a point, okay? But a basic solution may not be a feasible solution, okay? The reason is I only say all the equality constraints are active. I didn't say anything about the inequality constraints, right? If you arbitrarily pick an active equality, right, some of the inequality may be violated, right? So I will show you a trivial example in the next slide. Okay, and then we see X star is a basic solution that satisfies all the constraints, then that is a basic feasible solution. Okay, so in summary, a basic feasible solution, first it has to be a feasible solution, right? Second criteria is out of all the constraints, there are n linearly independent active constraints. Okay, because n linearly independent active constraint will uniquely define a point. Right? That's some result you learned from linear algebra. Okay.
Real quick.
Yeah.
So like whenever we're talking about equality constraints versus like inequality constraints, would like a greater than or equal to,
yeah,
would that fall under like equality or inequality constraint?
If you have a greater than equal to?
Or like or equal to, yeah.
Yeah, so if you don't have the same equality as less than equal to, that is an inequality constraint, right? If you have, let's say, A transpose X greater than equal to B, you also have A transpose X less than equal to B, then that is, you can reduce that to an equality constraint.
Okay.
Right, yeah.
Got it.
Okay, so here's an illustrative example of a basic solution and basic feasible solution. Okay, so all these three constraints, are there three? Yeah, I think there are three constraints in this figure are inequalities. Right? There are no equality constraints. So here, as you can see, E, D, C, and F are basic feasible solution, right? Because they are feasible. Second, at those points, two linearly independent constraints are satisfied, right? We are in 2D. But what about point A and B, right? So point A and B are basic solutions, but they are not basic feasible solutions, right? So if you look at point A and B, two inequalities are active, right? But they are not feasible because they violate other inequalities. Okay, so that's sort of a geometric intuition of this concept. So now with this definition of basic feasible solution, as you can imagine, if I give you a polyhedral set, can you find all the basic feasible solution for me? If so, how do you find all the basic feasible solution? Again, the definition of the basic feasible solution is among all the inequality constraints and the equality constraint, there are n linearly independent ones that are active. Okay? So in total, I have m constraints. Right? So how do you find all the basic feasible solutions? Yeah.
Would you be able to like solve a system of n equations and all the solutions to that would be your set of vertices?
Yeah, exactly right. So what you can do is, there are in total m inequalities. You can enumerate all the possible combinations, right? So choose n inequality out of the n total number of inequalities. if the inequalities you choose happen to be linearly independent, then you make them active, right? So now since they are linearly independent, the solution to those active constraints are unique, right? And m choose n is a finite number. Once you enumerate those m choose n number of combinations, then you need to find out among those m choose n solutions which are the feasible ones, right? You can check, just get those solutions and check each of the inequality to see if they satisfy all the inequalities, right? Okay, so that already gives you a sort of a very naive algorithm to solve linear programs, right? If you have a lot of computational power, you don't want to design a smart algorithm, you could just enumerate all the basic feasible solutions and pick the one that gives you the best solution, right? But of course, this is not very efficient, right? Okay, so this is a main theorem I want to prove in this class, which is the equivalence of extreme points, vertex, basic feasible solution, right? So now we will show it in the following way. We will first show you A implies B, then we show you B implies C, then we'll show you C implies A. Right? So if you show this in 3 steps, you can show all these 3 concepts are equivalent to each other. Okay. So let's first do A implies B. Right? So whenever you want to write a proof, a proof has to be done in a mathematical rigorous way. Right? You need to write an algebra way to saying this is rigorous and so forth. But then how do you get an intuition? Right? Sometimes it's not so intuitive. Right? It will help if you first get some geometric intuition and see if your geometric intuition is correct and verify that in an algebraic way. So first let's say we say X star is a vertex, right? Remember what is the definition of a vertex, right? So if this point is a vertex, then we know that there exists sort of a half space C, right? So C transpose X star. Yeah, so let's say this is a polyhedral set. We know that there exists a C such that for all the X in this polyhedral set, and X is, let's say this point is X star. X is not X star. We have C transpose X star strictly less than C transpose X, right? So this is a definition of a vertex. And then the argument, the first proof is that we want to show if there exists a C that separates the polyhedral from X star, then it has to be an extreme point, right? So to show directly a point is an extreme point is not so easy, right? Remember, the definition of an extreme point is there doesn't exist 2 points whose convex combination gave rise to this particular point, right? So showing some point directly, showing it in the forward way is not so straightforward because you need to check every point. So if you need to check every point, that's hard. Then you know that you should do the other way around, proof by contradiction, right? So you can show that if a point is not an extreme point, then it is also not a vertex. It is much easier to show, right? So let's say if we have this point is not an extreme point, then that means you can find 2 points whose convex combination give rise to X star, right? So if you want to draw it here, it will be something like that. There exists 2 points in a polyhedral whose convex combination give X star, and then somehow you want to show that it violates this statement, right? So if it's not an extreme point, it's also not a vertex, right? So let's just state the contradiction here first. So the the contradiction is the following, right? So if X is not an extreme point, then there exist, let's say, Y and Z, both in P. And then Y is not X star. Z is also not X star, right? But then X star is a convex combination of Y and Z. Right? So now, the other thing we know that is if you want X star to be a vertex, then we have C transpose Y must be greater than C transpose X star, right? And then C transpose Z must be strictly greater than C transpose X star, right? So this is a definition of vertex, right? If X star is a vertex, then the statement is for all the points in the polyhedron that are not X star, they must be, C transpose X must be strictly greater than C transpose X star, right? Since Y and Z are in the polyhedron set, and then they are not X star, right? So then C transpose Y and C transpose Z must be strictly greater than, C transpose X star, right? So now, if you take that, we know if you use this fact, and then this particular fact, you quickly get a contradiction, right? Because according to this extreme point argument, C transpose X equals to lambda C transpose Y plus 1 minus lambda C transpose Z, right? But here, if you still want to satisfy the vertex argument, both of these terms has to be strictly greater than equal to C transpose X, right? Now you have a contradiction, meaning that if you assume X star is not an extreme point, you can show that it is also not a vertex. You cannot satisfy both together. Right? So if you want to draw a picture, that means somehow you cannot find 2 points on this side who are convex combination of whose convex combination give you X star. Okay. Any questions? Yeah, so let's leave a few seconds for people to absorb.
I have a quick question.
Yeah.
About like the definition of like a vertex.
Yeah.
So, like it says that your C transpose X star has to be like strictly less than anything inside the polyhedron.
Mm-hmm.
But like, what if? And I'm having a hard time wrapping my head around like, what if our vertex is on like the other side of the polyhedron?
Well, no, so the argument is like there exists a half space, right? So
Okay.
yeah, we will show you how to pick that half space later, right? So if you, later on we will show you, the last step is from C to A, right? So if you have a basic feasible solution that is vertex, so that is sort of a constructive proof. You will see how do we pick a half space such that it can always be separated from.
So we can like define the half space so that one side of it
Yeah.
is greater than.
Mhm. Yeah. Okay. Yeah, so it's like an existence argument. As long as there exists a C, then that is a vertex.
Okay.
Right? Yeah. But the extreme point is very hard to verify, right? Because you need to check any 2 points.
Yeah.
Doesn't give rise to that particular point. Okay. Yeah. Yeah. So now let's show B implies C. Okay. So B implies C, which is, I think it's extreme point imply a basic feasible solution. Okay, so how do we approach this problem? Okay, as I said, the definition of extreme point is very difficult to use, right? You have to check any combination of points doesn't give rise to the extreme point, right? So if you want to show extreme point imply basic feasible solution, the forward direction is still hard to do, right? So the either direction is if a point is not a basic feasible solution, then it is not an extreme point, right? Because showing a point is not an extreme point is easier. You just need to pick 2 points whose combination gave this point. Then that point is not an extreme point, right? Okay, so we'll show it the other way around. Okay, so first of all, we can easily observe, because any extreme point has to be feasible, right? The statement, the extreme point is a point within this polyhedron. Of course, it has to be feasible, right? So the feasible is the feasible part is given, right? Because any extreme point is feasible, it has to be a feasible solution, right? The hard thing is a basic part, right? Yeah.
So on the other slide, though, we had a shape where some extreme points weren't feasible.
No.
Right. If we,
So yeah. So that not
so
yeah.
Those
So,
ones aren't considered part of the polyhedron.
right. So these are not called extreme points. So these are called basic solution. They are not called extreme. Basic feasible solutions are extreme points. So if you go back to the definition of extreme point, right? First of all, it has to say X is in P, right? It is a point in the polyhedron set, right? So all the extreme points are feasible point. Okay. Yeah. Okay, so then let's still show by contradiction. Okay, so let's think about this point x star, right? If x star is not a basic feasible solution, then we should show x star is not an extreme point, right? Okay, so then the idea is, if x star is not a basic feasible solution, if we can construct 2 points whose convex combination gives x star, then you can show x star is not an extreme point. Right? That's sort of the logic here. Yeah. Now, if x star is not a basic feasible solution, we know that the number of active constraints at x star, at least the number of linearly independent active constraints at x star, must be strictly less than n. Right? So if you have a number of linearly independent constraints to be n, then that is a basic feasible solution already, right? So let's write down the active constraint at x star as a equal, right? A superscript equals to b equal, and then there are some inactive constraints. Let's write them as a superscript strictly greater than equal b strictly greater than equal, right? So because x star, we assume x star is not a basic feasible solution, this is a set of the active constraint at x star, and this is the set of inactive constraint at x star, right? So now since x star is not a basic feasible solution, we know that the rank of a equal must be strictly less than n. Right? that means if it's not a basic feasible solution, the number of active constraints should be strictly less than n. Right? That's by definition. Okay. So you'll quickly see that if you know linear algebra, you know linear programming as well. So all the results I show you are based on linear algebra. Okay. So now as I told you, it is a constructive proof, right? If you know these facts, you need to construct 2 points such that these 2 points convex combination give you x star, right? Then x star will not be an extreme point. So a quick observation is that if the rank of A equal is strictly less than equal to n, then we know that there exists a vector D that is non-zero, then A transpose A equal times D equals to 0, right? Because if A equal is not a full rank matrix, then you know that the null space of that matrix has a non-zero dimension. Right? You can think about from a geometric perspective, each of these equality will eliminate 1 degree of freedom for you. Right? So you are left with n minus the rank of A equal degrees of freedom. Right? So that's why you can always find a vector D such that A equal D is 0. Okay. Now, how do you find a convex combination? Right? So you can argue that since this equality strictly hold, right? If you perturb x star a little bit, then this equality still strictly hold, right? Due to continuity. Right? So you can argue that there exists an epsilon such that epsilon is small enough A plus epsilon D are still greater than B greater than equal. And similarly, if you perturb it a little bit to the other side, the strictly equality still hold, right? Because they strictly hold if you perturb x star a little bit. Let's assume epsilon is a number that is as small as possible, right? So if you perturb a little bit, these 2 points still satisfy the inequality constraint, right? And these 2 points, of course, they still satisfy this equality constraint, right? Because A equal times D equals to 0. So here you have find 2 points that is a whose convex combination gives you x star. Right? So this is your, you can define this point as, let's say this is your y, this is your z, right? So y and z are feasible, right? And then, and y and z are different from x star, right? Because you perturb them by epsilon, and D is a non-zero vector. And x star is a average of y and z, right? Okay, so that's the end of the proof, because you can construct 2 points whose convex combination is x star, then x star is not an extreme point. Okay, so let's give some time for people to absorb and see if there are any questions. Yes?
Our vector z, how can we be sure that even though we're subtracting a small amount, it still will be greater than b?
Yeah, so you can imagine, let's say, this equality strictly hold, right? Let's say in this this difference between the left-hand side, maybe the difference between left-hand side and the right-hand side is a small number, but it's non-zero, right? So you can always pick a way smaller number such that if you times any vector d, this number is still greater than or equal to 0, right?
Okay,
Because for any smaller number you have, there always exists a way smaller positive number, right? Yeah. So that's sort of the epsilon delta notation. How do you make the proof
and
rigorous?
because it's not the equality constraint. It's a,
Right.
it's
Yeah,
a-
yeah, because they are not active, right? You can always pick epsilon much smaller than the residual of that inequality. Okay. Any other questions here? Now, again, the last thing you want to show is a basic feasible solution implies vertex, right? So again, like I said, how do you define a vertex if, let's say, this inequality is A1 transpose X greater than or equal to B, A2 transpose X greater than or equal to B, right? So in 2D, this would be a basic feasible solution, right? Because two inequalities strictly hold, let's assume it is a feasible one. Right? I'm ignoring all the other inequalities in this figure. Now, how do you show that basic feasible solution is a vertex? Right? Again, geometrically, a vertex means you can find, maybe draw it a bit better. You can find a half space such that the whole polyhedron lies on one side of the half space, and this particular point is on the hyperplane. Right? Okay, so let's say this is a vector C, right, in this direction. So this will be a constructive proof. Right? Just by looking at this particular figure, let's think about how do we pick such a vector C to separate this extreme point. Okay. So as you can see, this is the direction of A1, right? This is direction of A2. Right? Intuitively, if C is a Corny combination of A1 and A2, right? So that means if the direction of C lies in between A1 and A2, right, then it will be able to separate that. If it doesn't lie in between of this, it will not be able to separate that, right? Okay, so that's sort of our geometric intuition. How do we show that in a rigorous way, right? So the intuition is that if you pick a C, that is a positive combination of all the active constraints, right? You may be able to separate this polyhedral set, right? So let's try to generalize in n dimension and see if our intuition is correct, right? So again, if you have a basic feasible solution, you have A1 transpose X star equals to Vi, right? So I is, let's say in this capital set, capital I, and then there are n of those active constraints. Okay, so let's just pick C equals to the summation of all the AIs. Let's see I in I. Okay. Right, so what is C transpose X star, right? So C transpose X star is equal to I in I, AI transpose X star, right? This is nothing but the summation of B. Right? So at X star, C transpose X star equals to the summation of B, right? So we want to show that this is a hyperplane. This is a half space we want. So how do we show that? We only need to verify for all the points in this polyhedron that are not X star, C transpose X star must be smaller than this number, okay? Or greater than, yeah. It actually doesn't matter, right? So we know that for any points, for all x, first of all the x need to, if x is feasible, right, it needs to satisfy AI transpose x. For all x in P, it needs to satisfy those inequalities, right? Okay. So because it satisfies these inequalities, we know that C transpose x must be greater than equal to the sum of BI, right? Because C transpose x is nothing but the summation of the left-hand side, right? So it must be greater than or equal to the summation of the right-hand side, right? Okay. And then in order for this equality to hold, I want to argue that each of these inequalities must be equalities, right? If one of these inequalities are strictly greater than BI, you will have a strict equality here, right? Okay, so now the point is, how many points will give you the fact that all those inequalities will strictly hold as equality, right? There is only 1 point because the rank of this whole matrix is n, right? Because if all those these inequalities strictly hold as equality, all those linearly independent constraints must be active, and there is a unique point, right? So therefore, X star is a vertex, right? Because if you pick any point that is not X star, you will have a strict equality, okay? Right, so this is sort of like a constructive proof. You construct a C vector such that it satisfies the definition of vertex, right? Because the definition of vertex is relatively easier to verify. Right? You only need to pick a vector and then validate that it satisfies the property of the vertex. Okay. So now that's the end of the proof. You could, close your nose and try to redo it yourself. Right? If you are very fluent in linear algebra, this shouldn't be too much problem for you. Okay. I'm going to run out of time, so let me accelerate a little bit. So those are the proof in tech notes. So with that, there are some corollaries to this theorem. As I said before, the number of extreme points, vertices, and basic feasible solution in P is upper bounded by M choose n. Right? Because there can at most be M choose n number of system n linearly independent active constraints. Right? And some of them could be infeasible, so then they are not basic feasible solutions. Yeah. So in some sense, solving linear programs is not really so-called continuous optimization. Right? You are enumerating a finite number of points. Right? In some sense, it is like a discrete optimization, because there are finite number of vertices you would enumerate. Okay. And then if you have a non-empty polyhedron, AX greater than or equal to B has at least one extreme point, if and only if there exist linearly independent vectors out of the M constraint coefficients. This is just the application of the definition. Okay. Now, there is a concept in linear programming I want to talk about very briefly. This is especially relevant if you are going to implement some algorithm, right? But nowadays, no one actually implement linear programming solver. It's already pretty mature, but that's a concept I want to show you real quick. When you read the literature, sometimes people talk about this concept, and you do want to know what that is. Okay? So this concept is called degeneracy. We see a basic solution is degenerate if more than n of the constraints are active, right? So we say a solution is a basic solution if there are n linearly independent active constraints. But there are some basic feasible solution or basic solution where there are more than n active constraints, right? So here's an example, right? So if you have a problem in 3D, right, there can if you have 3 linearly independent constraints, that will uniquely define a point, right? But this point, at this point, 4 constraints are active. Right? So that means one of the constraints happen to be active as long as the other 3 are active. Right? So this does occur in some of the problem. As you can see here, you have 1. This is first one, 2, 3, and then 4, right? You have 4 active constraints. If you pick any of the 3, that can already define this particular point. And similarly, if you have a point here in 2D, 3 of the constraints are active, right? So that is degeneracy, which means at an active, at a basic solution, more than n constraints are active. Yes?
What does that affect?
So that effect,
What's the consequence of that?
yeah, the consequence is when you design an algorithm, then you need to consider those facts, right? Which especially in simplex algorithm, you need to consider because which variable do you move as a basic variable and so forth, right? There could be some ways of doing symmetry breaking. Yeah. Yes. Yeah.
So like when looking at that shape on the left,
Mm-hmm.
if I'm looking at like point B on that, there are 3 active constraints
Yeah.
there.
Yeah.
The 4th wouldn't be active, right? So
Yeah. So B is not a degenerate solution.
okay, so so just because you have a degenerate solution, there could be other solutions that aren't degenerate.
Right. Yeah. Okay. So what does degeneracy mean in standard form polyhedron, right? So that's the main thing I want to convey, because if you talk about simplex algorithm, you need to think about degeneracy in simplex algorithm. And simplex algorithm applies to standard form polyhedral set, which is you write all the equality constraint together, and then all the inequality constraint as x greater than equal to 0. Right? So let M be the number of rows of A, right? Then this M number of constraints must always hold in order for the solution to be feasible, right? And for the rest of the constraint, if you can find n minus m of them, then that is already a basic feasible solution, right? But then if you find more than n minus m of components of x that are 0, right? Well, when x is 0, that means these constraints are active. If I have more than n minus m, that means in total there are more than n active constraints, right? Because these are already m active constraints, and then if you have another more than n minus m, in total you will have more than n. Okay. So just real quick, this definition of phases. What is a phase? A phase is a non-empty polyhedral set, and it is a subset of P where a subset of the inequalities are active. Right? So in an extreme point, there are n linearly independent active inequalities. A phase means they are a subset of active linearly independent inequalities. Right? So for example, the set P itself is a face, because if you consider this set, this full set P, no inequalities are active. Right? You want to define this full set P. And the extreme point is a fix because at an extreme point, there are n-linearly independent inequalities. Right? And then at these edges, there are one active inequality. Right? So therefore, those edges are also face. Okay, this is just a definition. If you don't do research in linear programming or integer programming, you don't really need to know that. But I thought I would just give the definition. So the next concept I want to introduce is called polyhedral cone. Right? So this concept is useful when you have an unbounded polyhedral set. Okay, so remember in the second lecture, we have defined what is a cone. Right? So the set C is called a cone if for all the x in the set C, lambda x is also in C for all the lambda greater than or equal to 0. Okay? So let's say the first orthon is clearly a cone. Right? Because if you pick any point here, lambda x should also be in this set, right? For any lambda greater than or equal to 0. Yeah. So a polyhedral cone is defined of this form, ax greater than or equal to 0. Okay, so let's think a little bit for 1 second why a polyhedral cone has to be defined in this form. Right? So first question is, why is this set a cone? Right, remember, you can just check the definition of cone. Right? For any x in this set, and then for all the lambda greater than or equal to 0, lambda x is still in this set. Does this set satisfy the definition of cone?
Multiply, divide by lambda.
Yeah, so you don't even need to divide by lambda, right? So if you, let's say, pick an x in P, right? We know that ax is greater than or equal to 0, right? So now it says, for all the lambda greater than or equal to 0, you can verify a lambda x is equal to lambda times ax, right? So since we have ax is already greater than or equal to b, ax is greater than or equal to 0, lambda is greater than or equal to 0, you are multiplying to a non-negative number, right? Actually, a non-negative vector with a non-negative number, right? Of course, this is greater than or equal to 0, right? So that is a short proof that this set is indeed a cone, right? So now I have another question for you. Okay, let's think a little bit about that. For a polyhedron to be a cone, do we always need the right-hand side to be 0? Can we have non-zero right-hand side, right? So can a polyhedral cone look like this, where B is not a 0 vector? So because this is a general polyhedral set, we see a polyhedral cone has to be in this form. Right? First of all, we need to show if a polyhedral in this form, it is a cone. Right? So then the next thing we need to show is that if you have a polyhedral of this form where B is not 0, it cannot be a cone. Right? So that will finish the proof. So why if B is non-zero, it cannot be a cone? Okay, so let's show it real quickly, right? You can try to think a little bit about that after the class. So let's just suppose, use the definition of a cone, right? So if x, so let's say if this is a set, if X is in P, right? Then we know that for P to be a cone, lambda X has to be in P, right? Okay. For all lambda greater than 0, right? So how do we show a contradiction if this satisfies B has to be non-zero? Right? So let's pick a B where Bi is non-zero. Right? So maybe pick a B. Let's say Bi is one of the element in the vector B, right? Where you have Ai transpose X greater than equal to Bi. Right? So now there are two cases that can occur. First is if Bi is greater than equal to 0, right? So it has to be strictly greater than. There are two. If Bi is not 0, it can be either greater than 0 or less than 0, right? So now if Bi is greater than 0, what would happen? Right? So because you can pick any lambda.
Lambda 0.
Yeah, you can pick lambda equals to 0, right? Then you get a contradiction because the left-hand side is 0, right? The right-hand side has to be strictly greater than 0, right? Okay. So now if Bi is less than 0, right? So how do we show this part? Doesn't seem to be so straightforward. You could pick Okay, let me think a little bit about it and then get back to you in the next lecture. Or maybe some of you have some thoughts. Okay, yeah, so let's skip this part for now. Now, I will introduce another concept called rays and recession cones. So consider a non-empty polyhedral set AX greater than or equal to B, and let us fix some y equals to P. We define the recession cone at Y as the set of all the directions D along which we can move indefinitely away from Y without leaving the set P. Okay, and then more formally, the recession cone is defined as the following. Okay, so that means if you find pick any point in this polyhedral set, and then there is a direction D, right? And then you can move indefinitely along this direction D, right? So the recession cone for this set is all the rays in this particular range here. You can move indefinitely along those directions. That is called a recession cone. Yeah. Now, okay. So now it can be seen that the recession cone is the same as this set AD greater than or equal to 0. Right? So let's show that real quick. So if these satisfy the AD greater than or equal to 0, then you can quickly verify that AY, for any y that is feasible, AY plus lambda D is greater than or equal to B, right? Because AY itself is greater than or equal to B, and then since AD is greater than or equal to 0, then you can pick any lambda greater than or equal to 0. Okay. Yeah. So now there's another concept called extreme race. So as you can imagine, there is an extreme point. There is also something called extreme race. That means the race that are, quote, extreme, right? So in this particular case, you can pick any race in this recession cone here, where the extreme ones are these two directions, right? So the definition of extreme race is that there do not exist linearly independent U and V that are in the recession cone such that D is a combination of U and V. Okay, D is not a Corning combination of U and V. Okay, so this definition is similar to the definition in extreme point because for extreme point, we say that there doesn't exist 2 points whose convex combination give you that particular point, right? And for extreme race, it says it doesn't exist Corning combination of 2 other linearly independent vectors whose Corning combination give you this direction D. Now, I'm not going to the details of this type of proof because we don't have time to do that, but these theorems can give you a way of getting all the possible extreme rays in the polyhedral set. Okay, and similarly, it's very similar to the way you get the extreme points. Okay, so first of all, if you want to get an extreme ray, it must be in this polyhedral cone. Right? All the rays that are has to be in this recession cone. And then consider all the active constraint in this cone. Denote this as A equal. Right? So A equal X equals to 0. Denote the subsystem of these inequality constraints that are active. So we say D is an extreme ray of C if and only if the rank of A equal is n minus 1. Right? So this is also intuitive because in order to get an extreme point, you need an active constraint that uniquely define a point. Right? So extreme ray is a direction. Right? If you want to get a direction, you need n minus 1 active constraint. Right? Then the null space of that matrix will be dimension 1. Right? And also remember, not only the rank has to be n minus 1, but you need to satisfy this constraint AX greater than or equal to 0. It has to be a feasible direction in the first place. Right? So this is sort of a proof of why that is true. Okay. Now, why are we doing all those definitions, geometric concept like extreme rays and extreme point, right? So the motivation is actually this theorem, right? If there is one theorem you want to remember in linear programming, that would be this theorem here called Minkowski well. So if you ask people what is the most important theorem in linear programming, they typically will tell you this one. Or maybe there's another one called Farkash lemma. It's not a theorem, but it is like a theorem. Yeah. So what does this say? It says for any polyhedral set P, it can be represented as the following, where the VKs are all the extreme points, and the RJs are all the extreme rays. So due to the characterization, we know that there are finite number of extreme points and extreme rays, right? Because it's just choosing a combination of the active constraints. So it says any polyhedral set is a convex combination of the extreme points plus all the conic combination of extreme rays. Right? So how do you really interpret this theorem? The way to interpret this theorem is that it gives you an inner representation of a polyhedral set. Right? So having said that, you can imagine the original representation of a polyhedral set is an outer approximation, because you describe a polyhedral set by an intersection of half space, right? Each half space will cut off some region, and then if you consider the combination of all the half space, it gives you an outer approximation of the polyhedral set. This theorem gives you an inner approximation. It says the polyhedral set is nothing but you take all the possible combination. If you don't have rays, right? So because infinite size set is not easy to visualize, right? So let's say if you don't have any rays, then that is nothing but the convex hull of the vertices. Right? So it is very simple to visualize. If you draw any polyhedral set, it is nothing but all the convex combination of the vertices. Right? So if you have rays, you need to add the conic combination of the extreme rays. Okay, and this inner approximation is also finite. So this sum is what called a Minkowski sum. So what is a Minkowski sum? That means if you want to sum these two sets, right? So a Minkowski sum of the two sets is you take all the possible elements in set A and all the possible elements in set B and then add them up, right? So this theorem is saying that a polyhedral set is a Minkowski sum of the convex hull of the extreme point and the conic hull of its extreme rays. Okay. Yeah. So let's quickly show some applications of this theorem. Right? I'm not going to prove this theorem. You would need a few weeks of lecture just to prove this. If you want to see that, you can take a class in linear programming. Right. So one simple corollary is if the polyhedral is bounded, it is a convex hull of its extreme points. Right? If it has any extreme rays, then it is unbounded. Right? You can move indefinitely using the direction of extreme rays. Okay. So the other corollary is also quite interesting. It says, consider the problem of minimizing C transpose X over a polyhedral cone. Then the optimal cost is equals to infinity minus infinity if and only if some extreme ray D satisfies C transpose D less than or equal to 0. So if this optimization problem over a cone is unbounded, that means there exists a direction D such that if you move infinitely over that direction, the cost will keep decreasing, and then it will go to infinity. Right? Since all the this whole cone can be represented as a conic combination of extreme rays, there are finite number of those. You only need to check finite number of extreme rays has whether it has negative product with C or not. Yes.
I'm sorry, I may have missed this earlier, but D is always defined as moving away from the extreme point, right?
Say that again?
Like,
Yeah. So the extreme ray is defined as the recession cone is defined as you could pick any point in the polyhedral, you can move indefinitely to the to this direction. It's not only the extreme points. Like pick any point in the polyhedral, you can move in this direction.
Gotcha.
Okay. Yeah. Okay. Now, here's another corollary, which is the foundation of the simplex algorithm, right? Which is the geometric intuition we gave you at the beginning, where if there exists a finite optimal solution, then you can show that there always exists, there is always an extreme point that gives you the optimal solution. Okay. So the corollary is saying if we are minimizing, right, and then P is non-empty, the optimal objective value is not minus infinity. Right? It means this objective value is finite. Right? It's not minus infinity. Then the optimal solution can always be obtained at an extreme point. Right? So why is that? You can see that from the Minkowski-Well representation, because if you pick any x, it can be represented in this form. Right? So first of all, we know that the objective value is finite, right? Then C must have a non-negative product with all the extreme rays. Otherwise, you can move indefinitely using the extreme ray direction that will give you minus infinity. Right? Now, having said that, why there exists a VK such that it gives you the optimal solution? Because any point is a convex combination of the extreme points, right? You already know that the extreme rays are not doing you any good, right? So therefore, you will set all the mu to 0, right? Because they have a positive product with C. Now you are left with a convex combination of extreme points, right? So you will pick the extreme point that has the smallest inner product with your cost vector C, right? And that should be your optimal solution. Right? There could be some cases where 2 or more extreme points give you the same inner product as C. In that case, you have multiple optimal solutions, but there always exists one that gives you the optimal solution. Okay. And this is the basis of simplex algorithm to solve linear program. Basically, simplex algorithm is a smart way of enumerating all the extreme points. So we will only tell you the cases where the objective value is finite. Right? So if you want to know more about linear programming, you can read this textbook, especially if your research is related to linear programming. Okay. And then I still owe you one proof, which we didn't finish. I will get back to you in the next lecture. Okay. Thank you.